Good. Thank you, Yongchung. So it's an honor to be a faculty member of KAIST and having a very nice time. I thank you for the hospitality, and I thank you. If it doesn't snow, I'll be very happy. The topic is, I thought I would do something which is sort of general, and so there are two aspects to the talk. So before I forget, I just wanted to say, okay. Well, we'll see. I give credit to the co-authors. See if I can do it on the left side. So the first is research with my former postdoc, Sung Ah, who's at Seoul University, and the two Italians from L'Aquila, studying L'Aquila at the moment, and doing the earthquake, and the university was partially destroyed. And this is work which I call classical Tikhonov. So Tikhonov, mathematician, 19, at least his work in differential equations, and the idea of rediscovered over and over the original Tikhonovs. Let me explain why the premise. So it started, Sung came to me and we were talking, and he got very excited about this. So people call it flux, which is swarm. Paper is entitled, and one in but I the same thing. Hong Kong at City University, and who was quite a well-known guy, worked with Kukas. Mel, of course, had a chair at. So, and we developed this model called of Kukas-Mel system. Kukas-Mel system, trying to get that if going with velocity vi and t is time, so this just says defines velocity. See that how do the birds act? Well, you see there's a damping mechanism because the birds, this velocity of the bird knows about the other velocities, including his, I don't know if it's a male bird or a female bird. Her will be very careful. Okay, his or her velocity, and you see sign. A nonlinear interval. Again, comes in, and this is the and Sung in his work. So I'll say what flocking is. Okay, of course, mathematical definition. I'm not a biologist. I don't need a biologist, so. The definition of flocking, the mathematical definition, difference of the birds goes to zero. So the birds are going along, but they tend to go eventually at the same velocity, at least the difference of the magnitudes goes to zero for all the birds. Okay, and the flock doesn't get too big. It has to be bounded. The flock runs out to infinity. It makes no. We need a bound over all definition of flocking. Okay. Well, that was one story. But then in the literature, as I was looking around, one summer at the Weizmann Institute, which is in the news today because one of the faculty, they're probably having a nice party in her honor. The chemistry building is right. So it's nothing. So this group in Germany, so Ebeling, and they have a at their university in Germany, and they also have so of course, and Cooker and Smale never referred to these guys. A little suspicious. Okay, so here's particle. So that really looks like a particle. Classical mechanics. They put in some damping. Well, sometimes it's non-linear damping. I just put linear damping because you get the idea. So, and I put in this epsilon small parameter. So what is the epsilon small? Well, that's going to give me, since flocking is something time asymptotic, I want some level control. So I could have redefined it. Us some parameter. So what's the parameter number? Okay, but the other is very simple, which is good for a colloquium. If you take the second equation and differentiate it with respect to time, which sounds a little stupid, you already course of so this is n and this is n. What number of dimensions of the system? But anyway. Derivative of the particle system. And what's the important thing to recognize? And this issue. Negative sign from would be the viscous term for them, as you would expect. Okay. Well, if epsilon goes to 0, it seems that it should very well be, okay, that we can, and we can do that legally by Tikhonov's theorem, because that's permissible as long as the sign here is this system is stabilizing. If it goes unstable or oscillates, then but this is the easy case, so we have this stability result. The singular perturbation limit is just to cross off this term. Okay. Which, of course, is giving the long-term asymptotics if I rescale the time here. I've already done that, so. Okay, so here's the the classical Tikhonov's papers were written about 1949, 1950, 51. They originally appeared in the Russian literature, but then they got well known in the popular literature around the world. Norman Levin wrote several papers on this idea as well, and they can be found in the literature of the 50s. But now it's in the textbooks as perturbations. Okay, so I say the yields that the particle system, which was the second one, will imply the Kuka-Smale system. So flocking for Kuka-Smale will yield at least an approximate flocking for the particles, because the two systems are within epsilon of in some sense. Let's see. So that's the part of the talk. So I didn't go right down at the that was the second case. Said in the Tikhonov stuff in that class, I should say, so what's the conclusion? Why the result? It says, look, there's theory 1 and theory 2, but in fact, the particle system was the more fundamental one, because we could derive the Kuka-Smale from the particle, and that somehow, at least to me, makes sense, because the particle one is somehow the physical one, the Kuka-Smale one was the ad hoc one, and you see how it arises just as a singular limit of the particle. The second thing I wanted to talk about, okay, is again with respect to small parameters, and but I call this non-classical average thing. We had this damping mechanism that drove things ended in single literature. Much trickier and more interesting. So this one is about non-classical averaging, and I'll explain it in a second. And the work has occurred in 2 publications. So let's get to the co-conspirators who's involved in the research. So is my friend Slemrod from Weizmann. I hope is celebrating this. He's also vice president at times, so that he really gets to celebrate. Okay, Yanis Kavrakidis from Princeton, me, and Idris Titi, who's both at Weizmann, half-time, and at UC Irvine. And then involved in the second piece of the research was Bill Gear, who also lives in Princeton. Was at NEC and retired from NEC lab. And Yanis Kavrakidis made him an offer. He says, I'll pay you no money, but you can come in and use the chemical engineering department. So, and since Bill Gear so it's very useful to have him as our computation numerical. Nothing. So, and this one you can also get this if you're interested. I have one downloaded copy with me, but again, it's available from me. I can always give you the electronic copy if you want. It's also been posted on the Mathematics Archive web server. Okay, so what's the issue? Again, it's a system of ODEs to start it. Okay, the vector. The small parameter underneath the f. Okay, so there's a small parameter underneath the f, and then there's another term, g. Okay, so which is an initial condition. Okay, and what's the point? Okay, the point is any book you the same. Break them up into a fast. But that's not how it is in real life. In real life, you don't know who's fast. So in the textbooks, they break them up that way. But in the real life, you don't know who's fast and who's slow. And then it's not so simple how to do the limiting process if you don't know. So that was what the project was involved was how to deal with fast, slow systems when you don't know who's fast and who's slow. All you know is the system looks something like this, that this is, looks like a fast part and, of course, a slow part, but it's not broken into that the G term, and if the usual way would be, this term would be absent, and it would be another system of equations, which would be the slow part. What's the system and the idea? And this isn't how it's written, but it's really good for, I think, it. So I keep it at a very straightforward level because the ideas are very straightforward, yet I think useful. So assume you have a conserved inversion. So some up and up function that's exactly conserved for the fast. And you differentiated v along the fast part, just this piece, okay? Then you should get 0 in the time derivative, which is saying nothing more. The derivative of v should be 1,000 up for the f, the fast part. Okay, so this equals 0. We call such a v a macroscopic observer. And why do we call it or a measurement? And why do we know that? Because the classical ones, if this is representing the Boltzmann equation, okay, then if you do that and write down the moments of the Boltzmann equation, indeed that will be held true. Those things will be collisional invariants, and you would see that the density, momentum, and energy will be preserved quantities. So it's motivated in the back of our minds. We're thinking about the kinetic theory of to use that. Okay, so what's the interesting case to us? And the fact that there's no relaxation, no damping. So we're particularly interested in the case when the fast system here, so neglecting the G, okay, has rapid oscillatory. And I do have examples, so we'll get to that. But the theory is maybe do that first. Okay, so as I said, okay, differentiate V along the trajectories of the differential equation, the system of differential. Zero. And all that's left over is the gradient of V divided with G. So we put those two together. I throw away this term. So it's just the gradient of V changes. V changes with respect to time according to this elementary computation. And matched asymptotic expansion, you could not to write u sub epsilon as a perturbation expansion to leading order, so it looked like u0 and then an epsilon u1, etc. So we would try to expand it in a matched asymptotic expansion. Okay, so what would we see? Okay, we would see that the first term, of course, would satisfy just by plugging in, okay, to the original system, then to leading order, because the G was had a term of order epsilon. The dominant term, of course, is just the one with the 1 over epsilon, because that's a big number. So the dominant we see is this one. So, of course, that means the first term of the expansion just satisfies the fast system. Okay, that's rather fast. In the expansion, it's a function of t over epsilon, which I can call S. So this says u of 0 of t over epsilon is just u0 of S. And what am I making an assumption? And as well to infinity. So it's bounded. So oscillating around in n-dimensional space. Okay, so what does that tell us? Okay, so what does it tell us? So now, of course, I'm going to want to pass through the limit as epsilon. That's a little tricky because it's oscillating around this limit. Okay, but that's mathematicians do such complex. And we're coming from a PDE background, which is helpful. Okay, so that's why this is the sort of stuff that's not in the textbooks. Okay, so we have these fast guys running around. The first term in the asymptotic expansion, it's running around, and I assume on a finite interval, okay, it's bounded. Okay, so on the t interval, it's bounded. Okay, and hence it's a sequence of functions in R infinity in a compact set. So it's running around in phase space. Here's the compact set, and just a compact subset of Rn, and there the u epsilon around. We know I lose the battery? Maybe. Disappeared. Try it again. Okay, so then I'll point here. Try? Oh, bring a new one. Oh, then I'll tell jokes. Okay. I'll point with the... I'll point with... So then we have these guys converging weak star. So we know about that. I want to pass to the limit through the differential equations. So remember the epsilon, I have some differential equation, I want to pass to the limit. So you'd like to pass for a function f, a continuous function f. Okay. You'd like to pass that f of u epsilon from whatever the limit is, its weak star limit, which I called u sub super 0. Okay. Now in general, it's not true. Weak star continuous functions more or less are linear, so it won't be true for nonlinear functions. The standard example, say u squared, definitely does not work, because if you could non-convergence, you have non-convergence and weak convergence, you have strong convergence. So one would prove weak convergence implies strong convergence, what would be very nice, but I don't think they'd give you a Fields medal for that. They would notice that you made a mistake. So yes, in general. But what can you do? And here's a nonlinear function of a weak star convergence subset. These guys are bounded at L infinity. Okay, and it's nothing more than the Riesz representation about it. It says that there's a representor of the. Okay, it's a linear. You think that you have linear functionals on the, and the representer of the limit is this guy, nu, and it's called the Young. okay, and represented this notation is indicative. So you integrate f against the Young measure, and that produces the and the Young measure due originally due to my late colleague Young at the university. Also, the Young of Young's inequality. That was his parents in Cambridge. So, but not the Young modulus. That's it. Not a relativist. I was in the elevator with L.C. Young, and he asked me what I was doing, and I said I was doing something on Hilbert space, and he said, "Oh, I knew Hilbert," so I was very impressed. Okay. Okay, so let's go back and use the theory. That's the only analysis that's really used. Okay, but it's useful. Okay, so I had the original equation. Let's go back on instant replay. So I had the original equation. I differentiated with respect to time. The part with the f went away because of the because it's an observer, and so grad v dot f equals 0. So all I was left with was expanded epsilon. So to leading order, I see the solution to the fast equation. And I integrate both sides of the equation with respect to t, could hardly resist. And now we pass to the limit using the definition of the Young measure. Oh, push it up. Oh, very good. Okay, so we did the expansion. We integrate both sides with respect to t. The time variable, and now we pass to the limit here. Well, by the definition of the Young measure, this is v on the oscillating guy, so it's v integrated against the Young measure. This is just the data, which we kept fixed independent of epsilon, so that just stays wherever it is. And this one, we just pass this limit again using the definition of the Young measure. So again, by the same definition, it has to be grad v dot g integrated against the Young measure, and then integrated with respect to s. So it looks like in the limit we produced an ODE, just an integrated form. But it's not quite, because remember the measure over here depended on the initial data, because it's given us from the sequence of the U's, the first U's. So it in fact depended on the initial data. So it's not quite an ODE, but it has this very pretty representation. Okay. In fact, if we this guy to be V0, you see, it has this very pretty integral representation. So it says nothing more that if you want to know V, the observer, say the density or the momentum or the energy at time t, you just have to integrate the V dotted with G, take the gradient of V dotted with G and integrate it against your supposedly known Young measure that you computed from this fast oscillation. Integrate it, and then you know how to update the system. Okay, I hope that's not too obscure. And now let's get down to the engineering part of the lecture. In engineering. So so let me and okay, so let's picture. So here's time. Okay. Here's a short interval, say 0, 1. This could be 0 to 1,000 and 0 to 1. So how do we? So it's them. Okay, remember, I know how to compute V in time t. So it says run your system, or fast system, the fast system, for a very short time, say of length 0, 1. It's oscillating around like crazy. Okay? Sample enough points to get a good estimate of the Young measure. Okay? Okay? Now you know V at time little t1. Okay? Now do the same thing. Start with a slightly different initial data and run it a little longer time if you want, up to a nearby time via time t2. Estimate. Okay, you've estimated the Young measure over here. You've over here. So you've estimated via time t1, via time t2. Let's say in this interval, okay, via time half and 3/4 or something like that. Okay. Now when in the old days when I was teaching on, what I taught them make a tangent approximation, and we always tell the students Euler's method is very useful for learning in a first course in ODEs, but you never want to use it in real life. Okay. I mean, would you want to use Geer's method? Oh, he's one of the co-authors. Or you use something really, Runge Cutter, all these methods. So you never use Euler's method. What do we do? Okay. So you have via time t2, you have via time t1, so you can approximate the time derivative by taking the difference of via time t2 minus v of time t1 and dividing by t2 minus t1, which is nothing more than computing the slope here. Okay? And that gives you an estimate for dv dt. Okay. So instead of approximating the right-hand side of the differential equation with the f, you approximate the left-hand side. Okay. So it's a little different than the usual. Okay, now we can have a big step. Okay. Okay. Because we know v, so we have and we can say, oh, v over here is approximately that. Okay, and we can do similar thing and do a v over here. So we can, again, so we have v over here, and we can then do the same thing. We have to start the system all over again. Now v all the way up to here, and now we have to start all over again. Well, we have to start all over with the micro small data, the u's. Find a bunch. The literature and the subject called the lifting step. So you have to lift this data from the v, which isn't too much information, and find a bunch of u's that will fit the v's. So you do a lifting step that tells you how to make a reinitialize the program, and then you do it over again. So I'll say it again in words. You let the system run around, you find the chord, you lift, and do it over again. Okay. What's the advantage? Okay, why did I do it? Because to solve the original equation d dt of u epsilon equal plus the j, okay, or if you want to think of it, the u dt equals f plus epsilon g, if I rescaled, to account for the epsilon, under the usual story, you have to work with time steps of order epsilon, very small time steps. Here we work with small time steps. So in the language of numerical analysis, the small scale is never resolved. We don't have to resolve. When I think about Navier-Stokes, it would say on those large, it's sufficient to just sample the Euler, and if it's a small viscosity, you never have to resolve the small viscosity. How am I doing for time? Go on. Okay, so I hope it'll become clear if I do an example. So here's the example. The example is a system of ODEs, and I'll say where it came from in a second. So it has a quadratic part, and then this is just a second order divided difference. So that's approximating the Laplacian. So two derivatives with respect to x here, and this is some nonlinear term. And we'll see where it came from in a second. And I'm going to assume that this system of ODEs is running periodically, not in time, but periodically That is if you go out n steps, you come back on yourself. So let's account for periodic boundary conditions if it becomes a PDE. Periodic boundary conditions. And then I restate what the h is. It's the length of the interval, 2 pi divided by n. So where does it come from? If you do a usual discrete version of this KDV-like Lewis equation, you'll end up with this one. So it's not quite the KdV equation. Why isn't it not quite the classical KdV equation? Because there's a u which hits the u triple x's. So at the PD level, it's terrible, but at the LD level, okay. Now I didn't. We'll give credit on the next slide. So that's going to be the example, and I'll say more about it in a second. But it's somehow the paradigm, well, that's the example I can think of for a system which has slow hand side from the viscous term and fast oscillations, u triple x term from the KdV. So it's a very rapidly oscillating KdV part and then the slow diffusion. Now, this would be the and but if you wait and you want to gets affected. So you want to see how the diffusion acts, but you don't want to take little epsilon steps to get there because that'll take you forever. Okay. So it has the fast and slow part. Here's the fast, here's the slow. And I actually wrote it down in gory in details, but that's not important. Now remember, to make the idea work, we needed these macroscopic observers. I needed lots of guys who are conserved by the fast system. Well, that's one of the reasons for using this example, because if you set the u sub k is equal to a sub k squares, and then look at the fast system, there it is, and then you, where I've redefined the time by yet another variable s, okay, this is, and that was written down by, of all people, Peter Lax, in the beautiful 1988 paper, one of my math to read. I get a written as a matrix system. The LDS, where L is a matrix, where you have the commutator BL, so BL minus LB on the right-hand side. So if you equated the entries in this matrix, you'll get that. And that's a wonderful. If you haven't seen it before, probably you have. I'll explain why anyways. Okay, so there's in this example for n equals 6, that's what L looks like, okay? Which is this Jacobi cyclic matrix. Okay, so what's so good about Lax pairs? Well, let's just do, how does L squared change? So DDS of L squared, so it's L times L, the matrices. You plug it in, you get BL, it's the commutator of BL squared. In fact, it's the same for any power P. So DDS of a L to the P is BLP, so it's B L to the P minus BB. Well, P equals 1, 2, 3, you don't get any information. Okay, but for P equals 4, 6, on the even one, you take the trace of both sides, it's always going to be 0 here, no matter what. But for the even odd cases, it's the traces gives no useful information. But in the even cases, we then start reproducing for each power p, even powers. We've produced conserved values, because the trace here is always going to be 0, because the trace of AB is equal to the trace of BA. Okay. Okay. So the trace of the commutator is always going to be 0. Model problem has lots of conserved guys. That's because it's almost completely integrable. Okay. Completely integrable, but it's not even a Hamiltonian system. A few words about that. Okay. And okay, so I produce n over 2 plus 1 functionally independent invariants. And the numerics, at least Bill Gear's numerics, indicates that the list is exhausted. Okay. Okay. This also has a connection with the total lattice. If you set u sub k equal to e to the zk, system of these of these, which is the total lattice. Okay. Now, why doesn't the theory from the total lattice apply? Because the total lattice, okay, gives you information on the xk's, which in the periodic case are unbounded. So it's not obvious that, okay, you have a whole bunch of xk's which are unbounded. How do you know that the difference is going to be bounded? Issue, and Moser worried about this issue and for this problem in the periodic case, and it's some references there in the. Okay, let's get back to the story. It's getting late. Okay. Let's get to this one. I mentioned this one. Okay. Third one here. It says, if you were thinking but they have angle variables for those who remember their mechanics. And this says we only need the actions. We never have to find the angles. And in mechanics, classical mechanics, finding the angles is really a hard business. The formulas are terrible. You don't need the angles to do the averaging. Just the actions, the conserved guys, are enough to do the computation. So it eliminates, even if variables. Theory, it means you wouldn't have to actually construct the angles. Okay, let's get to the examples. Okay, so what will happen? So let me just run through some of the numerics to show what happens. So we run the algorithm, and what happens? Okay, well, first of all, here's what in the case n equal to 6, here's what the, of course, I can't draw a picture. So project it into three-dimensional is doing, and it looks like it's running around on a torus. Okay, and having a good some initial values, and okay, shows you that exactly how the fast system is running around. If I plotted the fast system, it's just components of the fast system, and again you see it's oscillating like crazy, as I expected, so it makes the interesting case. Okay, that one's not so easy, so interesting. Okay, this one is this is the evolution of the right-hand side of the equation. Okay, for one of the invariants started with g. So this is a grad v dot g for one of these n over 2 plus 1 invariants, and you see it's oscillating like crazy. But remember, in our theory, we're going to average it over the Young measure. And here, when you average it, you see it's quite stable and very nicely behaved. Okay, now let's get to the proof of the exercise. So let's agree what the problem is. And then I stop. Because if you're thinking about Navier-Stokes, it's as good as example as any. You have small viscosity. Something like that. And so that's the expected guy. So it's, you want to wait a long time to see the effect of your viscous term. Okay, so here I draw 3 pictures for 3 different environments. Now, this is a punchline here. This is the okay. So now, if I take solution by solving the ODE without the averaging and taking little tiny steps and then plot the graph. So I ran the computer for a really long time. Actually, we ran Bill Gear's computer for a really just on a laptop. Okay. And you plot it and you get this picture. Then we run our method. Okay. Of each other. Method, okay, I think works. So what does it say roughly? Okay, the smaller the epsilon, the better the method. Okay, because you. So how big? And I gave some numbers here, but I think someplace. If I reduce by a tenth, I think it's on the next page. I'll say it in words. I think we have it here someplace. Okay. Okay, so I won't say it here. Let me just say, I think, so if you reduce epsilon by a tenth, okay, that means 40 times faster than the other one. The smaller you make it, it goes up by orders of roughly a 10, or 10 over. So for each time you decrease epsilon, make it smaller, our method will be 10 times as fast, roughly, which is pretty good. So what's the method good for? It's a good place to stop. So it's particularly useful for systems to see long of a viscous behavior called finding the effective viscosity. But you don't want to compute forever. You're in a rush. Okay. You just say, okay, I can do it by taking these big time steps. So that's it. And it works quite well. If anybody has other examples, it's a good place. Okay, I promise to stop early, just like I always do, because people have to go home and see the. Thank you very much.